everyone. How are you this evening? Good. I'd like to introduce you to about 10 trillion of my personal friends. These are Ecoli Bacteria. Right now, they're digesting my dinner. They're doing the same with you. I've studied these little creatures for decades, and I love them. They're absolutely wonderful little organisms. They've taught me so many things about life, the universe, biochemistry, etc. These are actually the first organisms that were on the planet, as far as we know. They're about 4 billion years old, and guaranteed they're going to outlive you. This is what they do. They grow and divide, grow and divide. As long as they have food, they essentially double about every 15 minutes. They're absolutely beautiful little creatures. Now, I like to think of them as computers, chemical computers. They're constantly sensing their environment. They're constantly adjusting their metabolism. Literally, they're going through their day living, sensing, growing, changing. It was a really odd perspective to have that cells were computers not so long ago. But in recent years, people have started to understand that the architectures of biology, in fact, match very closely to the architectures of computing systems. This is because we've built computing systems over the last 40 years, and we've started to see that in many ways we're retracing the paths of evolution. Over time, there's information sharing across these two domains. We're starting to learn from biology and bring in traits into computing systems, things like self-repair, things like adaptive programming, genetic algorithms. And it goes the other way as well. We're learning how to make biology into structured circuits. We see all this through a lens of code, of software. We call it DNA. DNA is actually something that we've known about for 60 years. We've understood the structure of it, but really we haven't had a window into looking at it until we started sequencing it, until we started to read the code of life. And a lot of this came about because of the Human Genome Project, which focused scientific attention globally on the challenge of reading DNA and learned how to amplify the process. Essentially, what we do when we sequence DNA is we pull out the chemical molecule, which contains digital information, and we translate it into electronic files. It's that simple. We've automated the process since we completed the human genome. We have machines now that literally are factories, churning 24/7. Reading DNA code, not just of humans, but of every living thing on the planet. And we're generating this data incredibly fast. We're used to the idea of Moore's law with computers, the fact that computing power doubles per dollar each year. What we've learned with reading genetic information is that it's not just doubling each year. For about the last 6 or 7 years, we're getting a 10-fold improvement per year. In other words, we've never made a technology that has ever gotten so powerful, so fast. $1 billion to read a human genome 10 years ago. Today, you can put it on your credit card. And chances are, you're not out seeking it yet. You don't even know what it's good for. A few people have been sequenced in this room, perhaps, or maybe sampled with something like 23andMe. But what do we use this data for? In fact, we're collecting so much data, none of it is human readable. We need really artificial intelligence to start to link this information together, to start to make sense of it, and also to map it back onto the traits of who we are or the various organisms, what they do, how they work. This is one of the most fascinating fields of biology right now. It's called systems biology, and it's literally reading the code of life. We're learning faster than ever before. about the living things that we share our planet with. We've never had a view into this world before. In fact, even the microbes that I just showed you, we didn't know they existed 400 years ago because we couldn't see them with the naked eye. We only associated them with disease 100 years ago, and we still don't know, in large part, what their natural function are, what their normal functions are in our bodies. We are still very naive about the most fundamental thing in our lives, our life. I'm going to jump back a year, 2010, to something that I consider to be one of the most significant achievements humanity has ever done. These two gentlemen led a scientific team that made this little creature, a bacterium. Doesn't look like much, a little blue colony on a plate of growth media. And yet these little colonies set off a firestorm of media attention around the world. They gave it a really, really terrible name. Mycoplasma mycoides JCVI Syn 1.0, a name only an engineer could love, only a scientist could love. The media, thankfully, rechristened it Cynthia. It is the world's first synthetic organism. The Economist magazine published this story, and man-made life. The computer being one of the parents of this little creature. And I love the byline so much. Artificial life, the stuff of dreams and nightmares, has arrived. Now, this was a year and a half ago. Obviously, the world didn't end because this little organism came to life. And in fact, we haven't even seen 1,000 new organisms follow in its path. But they're coming. What those scientists did was essentially reverse the sequencing process. They took electronic code, a file on a computer. They turned it into DNA, and they booted it inside an existing cell, transforming that cell into a completely new creature. In computer terms, that's like taking a computer that runs Windows, reformatting the disk, loading Linux and booting it up, and now it's a Linux machine. Not all that difficult conceptually, but an amazing achievement scientifically, and we'll keep building on that. This is what that organism's genome looked like on the left. That is the design of its genome, of its program. It looks a little complicated, but really, the scientists just copied it from what nature had created. Nature writes incredibly powerful, robust genetic code. The tricky part was actually synthesizing the DNA and assembling it. No one had ever written this much DNA in one go. It was about $1 million worth of DNA synthesis. And they had to devise whole new ways of stitching it together, which they did. It's called Gibson assembly. And it's absolutely brilliant. What we've been able to do then with this achievement is go from bits, electronic data, to atoms, real-world DNA, to biology. I think it is really the most powerful technology humans have ever created because it literally allows us to program living things. We've never had this before. We've been able to breed living things. We've been able to select for certain traits, but we've never been able to do this directly from computer code and make something new. This little organism got a front page cover on the journal Science. This is like a supermodel getting the cover of the Rolling Stone. All synthetic organisms in the future will want this. It doesn't look like much. But again, the bottom line is life has become programmable. It has become something that we can literally start to decide what we want it to do. We can put in functions, and we're starting to build new tools to make this easier and easier. This is a world-changing technology. It will reach into every single area where life exists, where biology operates. It will literally change our planet. Now we have to ask ourselves, what is it that we want to make? Before we were just stuck with whatever came about. But now we get a choice. We've actually moved past Darwinian selection, and now we have to think, oh my God, what do we want? There are limitations right now. The techniques for printing DNA, to go from electronic data into the DNA, it's still crude. The technology is generation 1. We can't stitch together a very large genome yet. And it's still pretty expensive. We literally pay per character as we're building the DNA. And right now it's about 20 cents a base. This is an exponentially decreasing cost. It's falling rapidly, but we haven't quite shifted over to the next generation equipment. But more than that, there's what can we make and bring into the world safely, that has economy, that has value, that can get past the regulatory barriers, that can get past the intellectual property barriers. This is the challenge now in building this new next-generation biotechnology industry, this industry that's accessible to virtually anyone. Already, we're starting to make organisms that do things like make fuels. We're starting to think about new ways of making research organisms. We're starting to make new diagnostic tools. We're starting to make new drugs. These are all pretty standard. But we can think bigger now, because not only can we write code and mix and match code from any living thing, there is no species barrier, we get to control the environment that it grows in, just simply by putting it into a box. Already we're starting to think about how do we make organisms that can grow under Martian standard conditions, potentially making bacteria or something photosynthetic that can live on the surface of Mars. So one day we can literally bring organisms to Mars before we send humans. We're not limited by essentially just what life needs to survive. We can set up conditions where potentially enzymes, these magical little proteins that do the most complex chemistry that allows life to survive, to make things like diamond. We haven't done it yet, but can you imagine enzymatically synthesized diamond? It's just carbon, and enzymes can do the most amazing chemistry. Now, there's no natural reason for enzymes to do this, but we have much wider vistas we can explore. Already there's evidence that we'll be able to do carbon nanotubes. Again, making one of the most strong compounds we've ever developed. If we can do that enzymatically, it's fantastic. And perhaps even computer transistors. If we can make bacteria operate like transistors, we could potentially grow supercomputers just by adding sugar. Maybe they can run photosynthetically. This is amazing stuff. It's only limited by our creativity. Imagine grass that spreads the internet everywhere it grows. It's not impossible. We're going to see such creativity flooding into this area as new people. And as new people come into the field. And perhaps, and this is very serious, our genomes are not that big. It won't take that long to actually start being able to generate completely synthetic human genomes. I don't know where that takes us as a species, but I know so much changed between 1900 and 2000. We have to expect major changes between 2000 and 2100. We have to start thinking about this. I believe really that this is the most powerful tool we've ever made, and it's about time we started discussing it, talking about it, exploring it, teaching our kids about it. But before we can really fully explore the full potential of this field, we kind of have to get through this little shadow, this little valley that worries people, and this is viruses, in a word. Just about every time I talk about this technology, people go, can't it be used to make something dangerous? And really what you're saying is, are we going to make a bacteria or a virus that hurts us? Viruses in particular are pretty interesting because they're just software. That's all they are. We're going to see, I predict, virus engineering becoming the new software industry. People will start to program viruses to do some very interesting things that we have a little trouble imagining today. Now, a few years ago, I decided that I was going to make viruses that gave cancer cells a cold. Now, it turns out people have been doing this for quite a while. It's the perfect vector. Make something that only infects a cancer cell, gives it a cold, the cancer cell dies. Normal cells are unaffected. And in fact, the cancer cells becomes a factory for more viruses. The thing that I wanted to do was crowdsource it. I wanted to make, viruses are so inexpensive. Remember, they're the price of a sneeze. I wanted to make specific viruses for one person and give them away for free. And I've been talking about this for 2 years, and we're approaching doing that in the next year. But there's a lot more things viruses can do. They can be gene therapies. They can actually fix problems. They can become antibiotics, specifically killing certain bacteria. They can do drug delivery. Virus capsids can trap drugs and then deliver them to various cells. They can act as catalysts, doing enzymatic reactions. And they make excellent diagnostic tools because they're so selective. This technology, though, as this one anthropologist pointed out recently, there is no reason that someone couldn't modify a virus, that you couldn't release it on an airplane, that it couldn't be used for terror. We're going to have to make something like Norton antivirus for the real world of biological networks. I mean, in fact, we're starting to do that. But mostly, I know that we will get through this period and understand this in a positive way because I believe in human nature. There's a lot of noise in our system sometimes. We try all sorts of strange combinations, but somehow we always persist and make the world better than it was the day before. We've done that. We've made mistakes, but we correct very quickly and we move on. This century, I think we radically changed the world, top to bottom. Make it more sustainable, make it cleaner, make it safer. And I think it's because we all start getting involved, not just programming computers, but programming a living world. Thank you.
Wow. Thanks so much. They're applauding for you.